enthusiastic geocacher and a security researcher, assistant professor at Purdue University in Indiana. So let's hear Matthias Peyer on new memory corruption attacks.
Thank you very much for the introduction. Thanks, guys. Wait with the applause for until after the talk. This is not just my work, but the work of a whole bunch of students that I want to give credit to at a whole bunch of different places, from ETH Zurich to UC Berkeley to Purdue University, and a bunch of other places. And I want to specifically call out Nicolas Carlini, who did a lot of the coding work. And this gives me the opportunity to give you a little bit of a peek towards a demo that I will do at the end of the talk. And we will drop something interesting at the end of the talk, so stay tuned. But this is not just a talk on memory corruption, but a whole journey that happened. And it can best be described as Dr. Strangelove, or how I learned to stop worrying and love the segfault. In the last couple of years, I've worked a long time with software and different forms of vulnerabilities, memory corruptions, and a whole bunch of bad things that can happen. And the world that we are currently living in is that all the software that we are running on our systems is unsafe and insecure. And low-level languages like C and C++ trade all the type safety and memory safety for a so-called potential of performance. They don't necessarily give you the performance, but they allow you to maybe get the performance, but you lose all the type safety and memory safety that you would get otherwise from safer languages. And the programmer himself or herself is responsible for all the checks that have to be coded explicitly in the source code. And if any of these checks are missing, then a program just explodes in your face. But it's not just a large set of legacy applications that we are running on our current systems, but also a whole bunch of new applications that are being written in C and C++ that are still prone to different forms of memory corruption bugs. And I just want to call out that even at companies like Google, where they look very closely to coding standards and code reviews, they still have a whole bunch of security vulnerabilities if you just look at the Google Chrome browser that is being pwned every single year. Also, while finding and fixing bugs is very important, there are just too many bugs out there to find and fix manually. So we have to protect the integrity of our systems through some form of additional safety mechanisms that are out there. And if you just look back at over the last 2 years, or the last couple of months, there have been a whole bunch of security vulnerabilities out there that are calling for stronger and better defenses. And just to call out a few that made it to the press, there was Heartbleed that basically corrupted all the crypto keys out there on all the different servers that we were running. There was Shell Shock that allowed us to execute arbitrary commands on different servers. And there was Ghost, which basically allowed us arbitrary memory corruptions in any program that just did a get host by name call. So what we are facing is a huge amount of memory unsafety that our current programs have and that we have to deal with through different forms of additional security mechanisms and security guarantees. But let me take a step back and talk to you a little bit about the different memory safety problems that we are facing. So to give you some additional background. At the core of any security vulnerability, there's an invalid dereference, either through a dangling pointer, what we call a temporal reference, which is at one point in time, our pointer in the low-level language pointed to a valid allocated object, which was later freed by the programmer and is still accessed after the fact, after it has been deallocated. And the other alternative is an out-of-bounds pointer, which we call spatial memory corruption. That is, the pointer at one point in time pointed into a valid object, and then through the execution of the program started to move outside of the object and is now pointing into an illegal memory region, which is it moved out of the correct bounds of the object. But it's only a violation or invalid dereference if the pointer is read, written, or freed. According to the C language standard, you are completely free to have out-of-bounds pointers. You're free to have dangling pointers as long as you do not dereference them. And this makes finding these vulnerabilities and bugs so hard, because it only becomes a bug if we are actually using this invalid pointer, but not if we just have them in a program. And at any point in time, there are tons and tons of illegal pointers in the program, which is completely safe until you dereference them. And there are two types of attacks that build on these memory unsafety issues. And there are either control flow hijack attacks, where an attacker tries to execute some form of code, or inject new code, or just execute some different behavior that is not inherent to the original program. Or alternatively, there are data-only attacks where the attacker changes some data that is then used along the way of the program to change some internal state of the program to achieve a specific behavior. Today in this talk, we focus on executing code only, because this is usually the prime motivation of an attacker. An attacker wants to execute code on a compute platform to get additional capabilities on top of it. So how does a control flow hijack attack look like? Basically, in high-level terms, we can abstract a program into some form of control flow graph, and then the execution of the program follows this control flow graph and passes from one node to the other one, thereby executing the program. And in this sample control flow graph, we have a small loop and a condition that then breaks out of the loop. And the control flow of the application, as the application is executing, passes through this control flow graph, which is an abstract concept that compiler writers usually use. And it moves from one node to the other node as we are executing through the program. An attacker at one point in time might be able to modify a code pointer. Code pointers can be either function returns, indirect jumps, or indirect calls. These are all instructions that are used on our hardware to control how the control passes from one basic block to another basic block, basically from one node in the graph to another node in the graph. And if an attacker can control these code pointers that are then used in the program, the attacker can redirect the execution to a different location. So after modifying such a code pointer through one of the earlier mentioned memory corruption vulnerabilities, the control flow leaves the valid control flow graph and starts executing new instructions at a different location, and basically leaving the valid control flow graph. And the attacker can then reuse different parts of existing code that are in the execution image of the process, and either through return instructions, when it is called return-oriented programming, or through indirect jump or indirect call instructions when it is called jump-oriented programming. But let's switch the view a little bit and look at a particular code example. So we do have a small vulnerable function of a couple of lines of C code, and let's just assume that the attacker controls the two parameters given to this function, user and user2. We also have a function pointer that is being defined somewhere in this program, but the attacker can use these parameters that are passed to the function to actually override part of the function pointers we will see later. And the underlying problem is that the attacker can force an out-of-bounds memory write through this behavior by forging an out-of-bounds pointer and then dereferencing that pointer to write a specific value to this memory location. If you look at the stack or the memory layout of the program, we see the individual variables Q, we see the buffer, we see the function pointer, and we also have a piece of code at the bottom. So initially, in a valid execution, the pointer Q would point somewhere into the buffer, and the value user2 would be written into that buffer where it can then be used by the program in a legit way. But the attacker can use this addition to redirect the pointer Q to point to the function pointer, to the memory location of the function pointer instead of into the buffer. And as we continue, when Q is being dereferenced, the attacker can override this function pointer and then make it point into the code below. And as soon as the program executes or dereferences this function pointer which has been overwritten by the attacker in steps 1 and 2 before, the attacker can start executing code that is being controlled by the attacker and reuse different forms of gadgets. And these are basically the two building blocks that we have in current attacks and that attackers use to actually get control over the program. First, we have memory unsafety or memory safety violation that the attacker uses to build up the later steps of the exploit, and then the control flow of the application leaves the valid control flow graph of the application, and then the attacker executes arbitrary code. But we do have safety measures, right? There has been a plethora of proposals of different forms of safety mechanisms that have been added over the last couple of years. And we've got a whole bunch of different defenses that are active on our current systems. And let's just quickly go through them so that we can see where their limitations are and what other things are possible. So we started off with data execution prevention, where we removed the writable bit from several locations in memory and the executable bit from other locations. Before data execution prevention, we could just inject our new code somewhere on the stack or on the heap, and the attacker could just redirect the execution to these locations on the stack or on the heap and then execute this newly injected code. But with the advent of data execution prevention, attackers have to resort to already pre-existing code, as no new code can be injected into the executing image of the application. So this ensures that we can no longer just inject new code like shellcode or other pieces of code that can be used by the attacker to escalate his or her privileges. A second step is address-based layout randomization. Instead of allocating all the different pieces of an application at well-known locations, we just scramble these locations around every single time the application is started. And this makes it harder for the attacker to guess where the exact locations are. Obviously, this is prone to information leaks. If the attacker can somehow learn where these individual locations are, the attacker can build an exploit that actually can mitigate these defenses. We also have stack canaries that place strategic values on the stack that should not be overwritten, and safe exception handlers on top of that that guarantee that the exceptions follow a predefined pattern. So we've got a whole bunch of defenses out there that protect us from some of the vulnerabilities that are out there. But as we see with all the successful exploits on current software, these defenses are not complete and are at best partial and make attacks a little bit harder. But they do in no means stop the attacks. Also, ASLR, address-based layout randomization, and data execution prevention are only effective in combination if both of them are used together on the system at both times. Because if you break data execution prevention, you can inject new code. If you break ASLR, you know the addresses of existing code and can just stitch new locations and code locations together and then re-execute already existing code. As soon as you break ASLR, you can reuse these existing code locations. And I just mentioned before that information leaks actually enable you to infer the locations of specific pieces of code, and you can then stitch together the well-known code locations to gain full code executions. On desktop systems, such information leaks are quite common, and it is possible to find information leaks in different pieces of software. On servers, in the last couple of years, code reuse attacks have decreased, and attacks have gotten harder due to because there just aren't that many information leaks on servers. So this summer, we actually worked on an attack that leaks the ASLR, address-based layout randomization, base addresses of all the concurrently running virtual machines for different Windows versions and different Linux versions by using a memory deduplication side channel that many cloud infrastructures use. And we can basically learn the ASLR base addresses of concurrently running virtual machines by just generating random or well-known memory pages that just iterate through the available entropy bits of the ASLR base addresses and then learn these other addresses. But for more information, I would like to refer you to the paper and to the Wood talk. Also, the folks that worked on it, the two students or the two other folks that worked on it are here as well, and they can be reached to if you have questions. So the status of the deployed defenses is fairly incomplete. And we constantly see a lot of attacks that are going on and exploits are possible on current systems. But there must be some secret plan somewhere out there that helps us protect against many of these new upcoming attacks. We somehow have to defend against all of these new exploits. And academia has come up with hundreds of different proposals on how we can protect against these different forms of memory safety vulnerabilities. Many of them are very unpractical due to either a high performance overhead or other forms of overhead or incompatibilities with existing software. But two proposals that are gaining more and more momentum are stack integrity and control flow integrity. And we are seeing more and more deployment of these two defense mechanisms. But let's start with stack integrity. So we want to enforce an additional set of restrictions on return instructions. On the source code level, the return instructions are, or the return from a function to the caller is a very well-defined function. And it is usually a one-way function. You can only return to one specific caller at any single time during the execution of the program. But at the hardware level, this is not a restricted operation, as the return instruction is implemented on all the existing hardware architectures. It basically allows you to read a code pointer from the stack and then redirect the execution flow to an arbitrary code locations. And what stack integrity does is it takes the semantics from the programming language, from this high-level programming language, and enforces these semantics on the overly permissive instruction at the hardware level. So one example to enforce stack integrity could be to protect the return instructions through a shadow stack. So for example, if we do have these code snippets here that are where we can call foo from either function A or function B, we can enforce additional integrity on top of these functions, or on top of these returns. On the hardware level, as we are executing function foo, we can return to any byte that is executable or mapped as executable in the image of the executing process. But with stack integrity, we can enforce that if function A is calling foo, we will return only to function A as soon as we return from function foo. On the other hand, if we are calling foo from function B, we can ensure that foo will only be able to return to function B at this point in time. And thereby, we can ensure that the guarantees on the programming language level and the semantics on the programming language level will be upheld by the underlying executing program. And we can guarantee that the control flow never leaves this static, well-defined graph. The second security principle that I would like to talk about is control flow integrity. And control flow integrity at a concept level tries to ensure that the execution of the program never leaves the statically determined control flow graph. To ensure this security property, we first have to statically construct a control flow graph. And for each individual indirect control flow transfer instruction, we have to find the set of allowed targets at compile time. And at runtime, we execute an online set check. So for each indirect control flow transfer, we do have a check if the target is any of the possible targets that were determined at compile time. If it is in this set of allowed targets, we allow the check to continue. If it is not, then we terminate the application. So to show this to you symbolically, if we execute a function pointer, or if we execute a function through a function pointer, without control flow integrity, we can basically reach any possible executable byte in memory. So there are no restrictions on the machine level. Same for the return instruction. We can basically return to any arbitrary executable instruction. With control flow integrity, we add additional restrictions. So we first check the function pointer if it is in this set of statically determined targets. If it is not, then we terminate the application. Same for return instruction. We check the number, the current return instruction that is used at runtime against the statically determined set of allowed instructions or allowed targets at compile time. If it is in this set, then we allow it to happen. So this is slightly different from stack integrity that I talked about before, right? And we'll see a larger example in a bit. But what basically happens is that under control flow integrity, the attacker may write to memory at any possible time. And the underlying memory safety violation is allowed to happen. Only at a later point in time, this code pointer is verified when it is used. And there is some time between the underlying memory corruption that the attacker can use until the code pointer is checked later on. And there's something that the attacker can influence in that time window. But let's go back to the example on the two callers that both call foo. Under a control flow integrity policy on the stack, if A calls function foo, then foo can later return to either A or B. Both are valid targets. And the analysis that looked or searched through the code, through the source code, found that both A and B are calling function foo. So both A and B are allowed return targets when we're returning from foo. And maybe the attacker can use this to his or her advantage at one point in time to redirect the control flow to either A or B, as both targets are allowed at runtime compared to the statically determined set of targets. And this basically brings me to new forms or novel code reuse attacks. And I would like to start with control flow bending, which is joint work with Nicolas Carlini and Antonio Baresi that did most of the work, both at, one of them is at UC Berkeley, the other one at ETH Zurich. And the underlying idea is that instead of hijacking the control flow to a totally new location in memory, we just bend the control flow a little bit along a valid control flow graph. So we are not reaching new locations that are not visible in the program, but we are bending the control flow along the way. So if we look at an execution of a program, each individual control flow transfer is valid by itself, but the trace of control flow transfers is not valid and might not match the non-exploit case. So if you look at a trace, the individual control flow transfer might not be possible due to the different constraints that are upheld along the trace. But each individual control flow transfer by itself is valid. And this will allow us to circumvent static, fully precise control flow integrity, as we will see in a bit. The underlying limitation of CFI is that it is stateless. And each individual state is verified without any context. And control flow integrity as a security policy is unaware of all the constraints between the individual states. So any bending of the control flow along possible valid states is undetectable as according to what the control flow integrity policy can observe. So as an attacker, we have to search a path in this abstract control flow graph that matches the desired behavior of the attacker. And I'm not talking about some weak form of control flow integrity. Weak control flow integrity has been broken and is known to be broken. And there's a whole bunch of papers that were published at different security conferences last year that show that weak forms of control flow integrity is broken. And by the way, Microsoft Microsoft's control flow guard is an instance of a weak control flow integrity mechanism and can be broken by any of these mechanisms that were just cited here. It might make the attack a little bit harder, or harder in some cases, but it does not stop any attack from happening. So let's move to strong CFI and see what we can do under a strong control flow integrity policy. The assumption that we use is that we define a very precise, or the precisest possible control flow graph. So we assume that there is no over-approximation. And any possible compiler or compile time analysis will always have an over-approximation and thereby have imprecision along the way. But if we assume that there is no over-approximation and we have the most precise possible control flow graph and then show that this control flow graph is broken, then by design we can show that any possible CFI implementation can be broken this way, because even with this unrealistically overly precise control flow graph, we can still break it. We assume that there's some form of stack integrity for some cases, and thereby define fully precise static CFI, so that a transfer in the control flow graph or in the program is only allowed if there's some benign execution that uses it. So if we have a witness of an execution trace that actually uses this target, only in this case will we allow the target at runtime. Let's look at two possible forms of CFI. First, one control flow integrity form with and then without stack integrity. And for simplicity, let's start with CFI without stack integrity. So let's assume we have the strongest possible analysis on the control flow graph, and we have very small sets of possible targets for each individual indirect control flow transfer. What is the best attack that we can do under this condition? Ideally, we will resort to some form of return-oriented programming. And if we don't have stack integrity, the goal of an attacker is to find some path to, for example, system in this control flow graph that we have. And we have to find a set of constraints and memory locations that we have to write to divert control flow of the program along this path, which might be constrained through the memory vulnerability that we have. And as a second step, we have to control the arguments to system. And we might ask ourselves, what does such a control flow graph actually look like? And for a long time, we thought that this control flow graph is this super, super complex graph that is very complicated, and it will be almost impossible for an attacker to find a path from the actual vulnerability through this complex graph, and thereby controlling all the different arguments and constraints to then actually reach system on the other end. So the assumption is that it is very unlikely that an attacker will be able to find such a path. But what does a control flow graph really look like? In fact, we found that there's a large amount of functions that are basically connecting and densely connecting the control flow graph between all of these individual locations. There are all these functions like memcopy, malloc, and a whole bunch of other functions, or printf, that basically connect an arbitrary point in the control flow graph with another arbitrary point. These functions are called from everywhere. And many of these functions can override their own return address, or in a later point call a function that will then be able to override its return addresses. And under the control flow integrity policy that I presented before, as soon as we find such a function, we can return to any of the possible callers of this function and thereby connect two arbitrary points in this control flow graph, because both of these points will call this function. And then we can easily find a path through the control flow graph from the vulnerability to the system and then control the arguments, and the attacker wins. These dispatcher functions are often frequently called, and yet the arguments can be under the attacker's control through the different forms of memory corruptions that we discussed before. The dispatcher functions may override their own return address. So if you look at the simple memcopy call, where the attacker can supply the 3 arguments, we just use this memcopy call to overwrite its own return target and then redirect and connect these 2 parts of the control flow graph. Basically, we generate a shortcut through this control flow graph and then redirect the execution flow to that other part and can then continue on that other location. And we can basically supply the attacker data, which is the other location that called memcopy, overwrite the return address, make a shortcut, and then start executing closer to system until we can execute our code. So basically, control flow integrity without any form of stack integrity is broken. These stateless defenses are completely insufficient for the stack-based attacks that we present here. And such dispatcher functions are fairly frequent, and we can find different set of dispatcher functions that are basically being called from everywhere, both in the standard libraries that are supplied and used everywhere, but also in the actual code of the programs. The attack now becomes program dependent. So while the defense does not stop the ongoing attack, it makes the attack harder. And the attacker at least has to find the dispatcher functions and then find the shortcuts through the control flow graph. But the attack is still possible. So it looks like we are under some trouble here, right? But we still make the attack a little bit harder. So another attack that was presented fairly recently is counterfeit object-oriented programming. And this is not my work, not the work of my collaborators, but I found it a very neat attack that should be mentioned here as well. And the underlying idea is that a function can be a gadget by itself. And you can reconnect and tie together different parts of counterfeit objects to execute interesting behavior. So if we look at this C++ code here, where we define a small class, and we have this little destructor over there that is, of course, a virtual destructor. And the virtual keyword in C++ tells the compiler, hey, I want this to be an indirect call. And this allows us to redirect execution, because we just heard that indirect calls are the underlying principle for all these control flow hijack attacks. But then again, there's in this example, in this destruct, we just iterate through a list of students that will all be deallocated, and we call different forms of virtual functions on all of these objects that we have accumulated. Now assume that the attacker controls the list of students that we have, or the array of students. Then the attacker can suddenly generate a set of virtual targets and can reuse existing virtual tables to execute arbitrary behavior. And as a second step, use these different forms of virtual tables and connect them in a new way. And there are different forms of arithmetic gadgets. There are different forms of other gadgets as well, right? So for example, in this simple update score, we've got an arithmetic gadget that we can combine, and a memcopy gadget as well. Then attacker can just stitch together. Also, they presented an interesting technique that allows them to overlay objects. Remember, the memory is under the control of the attacker. And instead of just having each object by itself, the objects themselves can overlay each other. And the memory layout for a simple exam objects would, for example, look like as shown on the right-hand side on the screen. But the attacker can then use existing fields and overlay these fields with other objects, and thereby use different forms of arithmetic gadgets to, for example, update the virtual pointer table of that other object and redirect it to somewhere else. And through these object overlays, the attacker can just stitch together individual gadgets and then get different forms of arbitrary execution, arbitrary behavior. And this looks pretty bad if we combine these two attacks, both control flow bending and counterfeit object-oriented programming. But well, we do have a large amount of control flow integrity proposals out there. So we might want to look at how well they hold up against all of these different forms of attacks. And I picked out a bunch of different control flow integrity mechanisms that have been proposed either by academia or by Google or Microsoft and others. So there's lockdown that enforces a dynamic control flow integrity policy on top of binaries by using a form of binary analysis. So you don't need source code for that. There's MCFI and PyCFI, which are two forms of source-based control flow integrity that need a full compile time analysis of all the available code. There's Google LLVM CFI that has been recently released and is in the process of being upstreamed into the newer releases of LLVM. And there's also Google IFCC, which they presented last year, but have since redacted and removed from the source base. And we'll see in a little bit why they removed IFCC. And there's also Microsoft's Control Flow Guard. There are many, many others that implement different sub-policies of these CFI mechanisms here. So just to give you some context, when we're talking about CFI, the strength of the defense depends on the size of the equivalence classes that we have. And if we have a certain piece of code, we have a set of indirect control flow transfers. And these are the instructions shown on the left. All these instructions can be used by an attacker to redirect control flow from one location to an arbitrary other location. Any control flow integrity analysis will return a set of equivalence classes. An equivalence class contains a set of targets that are allowed at specific locations. And here in this example, I'm showing 3 different equivalence classes. And the last 2 call instructions are using the same equivalence class. So multiple indirect control flow transfers can map to the same equivalence class, and the same set of targets are allowed at these different indirect control flow transfers. And then there's the size of an equivalence class, which shows how much opportunity the attacker has to redirect the control flow to different locations. And ideally, we want to have many equivalence classes with a very small size. The smaller the size, ideally, the size of an equivalence class would be 1. In that case, the attacker would not have an opportunity to redirect control flow to an alternate locations. But at best, we want these equivalence classes to be as small as possible. So we looked at the precision on the forward edge, so for indirect call and indirect jump instructions. And we looked at the sizes of equivalence classes, and we present whisker plots where we show both the median with the red arrow of the sizes of the equivalence classes, the 25 percentile and the 75 percentile. But we also show with these little pluses on the side different forms of outliers. The different CFI policies are on the x-axis, and dynamic shows the amount of possible targets that are actually required at runtime. So we executed all these software or all these programs and measured how many indirect control flow transfers are actually used and how many locations. And if we look at all these different locations, we see that there's a surprisingly high amount of indirect control flow transfers with a surprisingly high amount of transfers or targets that is being allowed by all these different policies. And we see that under the dynamic policy, in many locations, only very few targets are allowed. And I would like to remind you that this is a logarithmic scale. So the higher up you go, the more transfers are allowed. Let me just point out a couple of interesting things. for IFCC, in many locations, the IFCC collapsed all the equivalence classes into a single set. So all the possible locations, all the indirect control flow transfers are allowed to use the same set of targets, which basically implements a weak form of CFI that allows you to reuse all the possible targets. And this is likely the reason why IFCC was removed later on. Also, we see that for lockdown, the spread is usually fairly big. So there's an outlier out there that has a very high amount of transfer that are allowed for a specific location. And this is due to the problem with the binary analysis, where we require additional symbols and information about the libraries. And there's usually one library out there that does not provide symbols, and then a large amount of transfers are possible due to limitations of the binary analysis. So you cannot recover all the information about all the possible targets in the code. There's also MCFI and PyCFI, and we see that for most programs, they actually provide roughly the same amount of precision. But PyCFI, which is per input CFI, sometimes restricts the amount of transfers that are allowed due to an additional runtime analysis that they do. There's also the new LLVM CFI, which is basically the second version of IFCC that Google recently released and will be part of newer upcoming LLVM releases. And it looks like as if it's much closer to the limit or the minimum amount of transfers that are being allowed than the old version. And it gives you a much tighter security bound. So let's look at a summary of all these different CFI mechanisms. And in the graph before, we've only looked at the forward edge. So how good is the precision for indirect calls and indirect jumps? But there's also the backward edge. And we've talked at the beginning of this talk a little bit about the backward edge and the importance of protecting the backward edge for basic control flow bending. And as we see, the first three CFI mechanisms, IFCC, Microsoft Control Flow Guard, and LLVM CFI, basically have no protection on the backward edge, except the already existing protections out there. And this basically makes control flow bending trivially possible and allows you to reconnect and stitch the control flow in any possible way you would want to do. For MCFI and PyCFI, there is some protection on the backward edge, and it makes control flow bending attacks harder, and we have to find these dispatcher functions and these shortcuts in this control flow graph. For lockdown, due to the strong protection on the backward edge that it adds, we have to resort to control flow bending on the forward edge, which makes the attack much harder. But due to the limits of the static binary analysis and the other binary analysis, we can still find possible targets. So it looks like as if the set of protections that are being proposed and are being integrated in current systems are fairly limited. They do make the attacks harder, and as soon as we add stack integrity to the mix, they will make the attacks much harder. So if we do have stack integrity, we can greatly increase the protection of current systems. But as we've shown before, many of the systems do not have stack integrity at all. So let's just for a second assume that we do have stack integrity. Then return-oriented programming is no longer an option. An attack becomes much harder. The attacker now needs to find a path through the set of virtual calls that are out there and resort to some form of restricted co-op. And the attack becomes really hard. An interpreter would actually make attacks much simpler. Assume that you have some piece of code that you can inject into the executing image of the application that even under the constraints of full control flow integrity still allows you to execute different code. And you would be surprised by how many Turing-complete interpreters there are. And I would like to introduce you to printf-oriented programming, where we'll show that printf is fully Turing-complete. and we can translate any arbitrary program to a format string. We can do memory reads, we can do memory writes, and we can actually implement conditionals as well. The program counter becomes the counter in the format string, and we can just move the program counter along. If we want to do loops, we can actually overwrite this program counter or this format string counter as different parts of the format, the string are being printed to the screen. And we can reset and jump around in this format string and then readjust our program counter to implement different jumps in this abstract language that we implement. And we are presenting a Turing-complete domain-specific language. And to make things interesting for you, I wanted to know, have you ever heard of brainfuck? It's like this fun Turing-complete language that only has 8 different symbols. You can move a data pointer forward. You can move a data pointer backward. You can increase the value on the current cell. You can decrease the value on the current cell. You can write a character to the screen. You can get a character. And you can jump conditionally back and forth. There's a format string statement for the incrementing the data pointer, decrementing the data pointer, adding, subtracting, adding a character, and even going back and forth. Depending on the implementation of printf, you can override this format string, the format string counter, and reset and jump around in the format string, which is what makes it dependent on the libc version that you currently use. To make things a little bit easier, we assume that we can call printf in a loop. So we basically either have to look at the current implementation of printf in the libc and override this printf internal data values by using arbitrary memory writes, or we just have to find a loop that loops printf in the current program, which we can usually do by in many of the programs that we looked at. And we can break the brainfuck interpreter into a simple fetch, execute, and retire loop that keeps executing by just calling printfs one after the other. So let me present to you a short demo on how we can translate arbitrary brainfuck programs into printf statements and then execute brainfuck by just doing a call to a single printf. So I have a set of small brainfuck programs, and let's just start with the Fibonacci thing. This is a small brainfuck program that just calculates Fibonacci programs. Let's compile the program, and we do have a the screen is a little bit small. I've shown the GitHub page so you can download the programs yourself and try them out. So we do run the printf Fibonacci program in a single printf statement, and we are generating different forms of Fibonacci numbers. And this is just a printf statement that we keep executing, and we keep executing this brainfuck program to just generate numbers. But there's another fun program Ever heard of 99 bottles of beer? It's a little bit longer program. So let's just execute this program and see what it does. And interestingly, you see that it gets faster as you're drinking more and more beer. As you're counting down the numbers and printing out the values, it gets much, much, much faster. There's also a game of life in there that you can play around with. There's a Mandelbrot fractal and Sierpinski triangle that you can print, all part in a single printf statement. So there's a lot of fun that you can do with this interpreter. And it's open source. You can use it, you can download it, you can play around with it, and it is available from today on. So go around, play with it, play with the Turing completeness, and let's see what happens. So let me conclude. Low-level languages are here to stay, and these low-level languages are full of potential. And as I've just shown, even with a single call to printf that can either be executed in a loop or by looking at the printf internal implementation, you can wrap around and show the full potential of these low-level programming languages. And weird machines are hiding everywhere out there. And with a single memory corruption, so if you do have either a format string vulnerability or a memory corruption that allows you to control the first argument to printf, you can get a Turing complete interpreter that allows you to inject your own little program. Without stack integrity, the defenses that we will add are broken, and we have to add stack integrity. But even with stack integrity, the attacker can still do a lot of fun stuff. And I encourage you to play around with the code that we've added. There's a simple Python script that allows you to translate any brainfuck program into a longer format string and a simple program. The format strings are out there. Go around and have fun. Thank you.
Thank you, Matthias. We have some minutes for questions, if any. So we got some microphones here. Any questions? Are you okay? So go home, play with printf. Okay,
I'll be around.
There's one question.
Hi.
Please.
Hello.
Yes?
Hello. It's working?
Yeah, it's working.
Okay. So thank you. Very good presentation. I have a small question. You use %10 in your printf programming, but in some implementations it's disabled. Do you have any workarounds?
There's only %n that gives you memory rights. So
okay.
in any of the libcs that we've seen, it's enabled. So there are obscure.
In fact, in Microsoft Visual C, I think it's disabled by default. You have to call special function to enable it.
Yeah.
Thank you.
Please leave or stay silent. Thank you. Please.
Yes, so I was wondering, I recently saw some discussion
Can you go closer to the microphone, please?
Hello, can you hear
Thanks.
me? Yeah. So I recently saw some discussions about, on the LVM mailing list, about something called SafeStack, where they...
Yeah, I'm one of the authors.
Ah, okay. I was going to ask your opinion on it, but I mean,
it's
that
good.
doesn't make any
It's
sense
great.
anymore.
We released an earlier version at OSDI. So the current version that made it into LLVM is a little bit restricted, and it's mostly geared as a debugging tool. But the underlying idea is to give you a tool that allows you to protect stack frames and give you stack integrity without any overhead. So I think it's great. It's a great tool, and it should make it into LLVM without all the additional overhead.
Yeah, I think it's awesome, so thumbs up.
Thanks.
Okay, thanks again, Matthias.
Thanks.
And see you soon. So we're back here in 14 minutes for console hacking. Thank you.